Hey, welcome. I hope you guys had a nice long weekend. And any of you guys get to go up skiing or anything? Nobody, huh? Oh, good. Good job. Hope to, but I didn't get to. Anyway, today we're going to be focusing on biophotonics tools. But before we do that, you remember we've so far talked about light sources, and you guys have looked at some of the properties of light sources with your spectrophotometers. We've looked at light-tissue interaction, but we're going to finish the light-tissue interactions with specifics. I have 3 more phenomena that lasers do when interacting with tissue that we're going to cover at the beginning of the lecture today. Then we're going to go on to tools, and then on Monday, you're going to get an overview, a basic biology overview. Next week is really biology, molecular biology, cancer week. Okay. So what you get next week is you're going to get an introduction to basic biology and the concepts and molecules that we work with a lot in biophotonics. You'll start to get a little bit more about fluorescence as well. And on Wednesday, you're going to get some molecular biology, so a little bit of a background on how some of these organisms can be modified to glow green when you expose them to blue light. And you're also going to get a primer on cancer and what cancer is about. We're going to have guest speakers next week. Anna Korbacha will be talking to you about all the biology-related things, and Frank Schwang, both people from the center, he'll be talking to you about the cancer piece. He's an MD, PhD, and so we'll bring you kind of a medical perspective on cancer as well. On Monday, I will be gone. You should expect for sure sometime next week you're going to get a quiz. Okay, we got to put the first quiz in there, so you will be getting one. Don't worry, it'll be about stuff that we've covered so far. And it will not be things that in theory you would have needed to study to remember. Hopefully they're the salient points. Okay? So with that said, let's finish our pieces. Let's think back to the 13th last week. We did the measuring hair thickness, which you guys are turning in the lab for today. And I will take all of your aggregate data and see if we can come up with any kind of rules about who has thinner hair, who has thicker hair. Last year, there wasn't a very strong correlation. Light interacting with tissue can be transmitted, reflected, refracted, scattered, and or absorbed. So we talked about that. And we specifically talked last week about absorbed light can cause heat, chemical conformational changes. We talked about fluorescence, and we talked about phosphorescence. Anyone remember the basic difference between fluorescence and phosphorescence? Phosphorescence lasts longer. Anything else?
Phosphorus and excited triplet state.
Excited triplet state. Anything else? Fluorescence was an incredibly fast process where you put in high energy light, and very quickly in nanoseconds, picoseconds, the fluorescence ends. Actually, usually in nanoseconds. Phosphorescence could last minutes. I was reading over the weekend that they're starting to come up with phosphorescent particles that they want to embed in the paint that is used for lane markings, because there's a lot of accidents that happen at night when people veer from their lane. And so now they're working on a technique to try to get, they would like to get like 7 or 8 hours worth of phosphorescence out of particles, and they put in those, the thing that they used to paint, the dividing lines. So I thought that was pretty interesting, that there are uses of phosphorescence all over. And then we went on to laser light can have following effects with tissues. First, we talked about thermal effects. And what we're going to do now is we're going to talk about mechanical, photoablative, and photodynamic effects. Okay, that's what I'm going to go into now before we veer off into tools. So, I can actually use a laser to create a mechanical effect. Okay, I can create a shock wave. I can push stuff with a shock wave. And when I do that, I can do things like creating a plasma. I can do explosive vaporization, so I cause a minor explosion. And I can also do cavitation. So these are things that we're going to talk about briefly. A plasma is basically with a very, very quick pulse of a very, very high intensity. So lots of photons in a very short amount of time. So incredibly high densities of energy. So something 10 to the 10th or 10 to the 12th watts per centimeter squared. Ionizes atoms and creates a plasma. Okay? Now, what that does is that boundary where the plasma is and where the plasma isn't, you get a very high pressure gradient, and this can create a shock wave. That difference in pressure gradient can create a shock wave which can cause something to break. So, if we have an exposure time, if we make that plasma, that pulse of laser light, very, very short, very quick, and we make it so fast that there's not enough time for that heat that's created in that plasma to be slowly dissipated through the tissue, then I get this process of basically a kind of like a destruction of the target, explosive vaporization. So this is what they use in the removal of tattoos. Right? So what are tattoos? Tattoos are tiny bits of colored pigment that's been put underneath your primary layers of skin. Okay? It's under. You know how we shed skin every single day? We shed a layer of skin all the time. Well, if you go underneath all those basic layers of skin and you put dye there, you can still see the dye through the layers of skin because they're very thin layers of skin, but it's there. It's permanent. Okay? So how could you get rid of it? Well, one thing you can do is you can try to make the dye particles smaller, with the hope that if you make them small enough, your body in its natural cleansing, there's cells are constantly bathed in fluid, in water, and there's blood, which is also in aqueous medium. And what you hope, we have the far end camera. Oh, great. That means we have a problem that we're not recording the right thing. All right. Sorry, 1 second here. Okay. Now we have a different problem. Well, I think we're going to give it one more try here. I don't think I'm going to be able to solve that very quickly. So there'll be a recording of you guys with my voice. Excellent. Okay, so when you want to remove tattoos, basically what you're trying to do is you're trying to get the pigment small enough so the skin reabsorbs the pigments and the color goes away. So what does that process look like? Well, here's an image of the skin, the surface, the epidermis, and the dermis. And what you do when you're making a tattoo, you're going in this layer here below the epidermis, you're going into the dermis and you're leaving the ink or the dye molecules, however you want to call them. Okay? So when you want to get rid of them, you take this laser and you basically have to blast very, very short pulses with very, very high energies such that they create a little tiny plasma right at the surface with that ink particle, causing a big, huge pressure difference, which then causes the ink to blast apart. Does that make sense? So you need to be able to go through the skin, and we know that skin is partially transparent to what colors? To red, and there is a little bit of transparency to other colors too, but to red it's more transparent. And you can imagine that the energy that you deposit here, the amount of heating that you can cause locally, is going to depend on how well that dye particle absorbs the laser beam. So, if you have a tattoo that has some nice dark spots, like a dark blue or a black, would that be easier or harder to deposit energy, light energy into? How come? Because black absorbs all the colors, right? So you can deposit energy. But if you have a nice area with a bright yellow, okay, or a white, okay, which you can actually do white in tattoos, right? You can do that. You can do all the colors of the rainbow in a tattoo now, okay? So if you have one of those old style, Army Navy tattoos that was dark blue or black, like they used to do a long time ago, those are easy to get rid of. But if you have a nice, colorful, fancy one like they make nowadays, those are much harder to get rid of because you can't get that pigment to absorb very much energy. So when you go through the process, this is a person that on the internet had shown the process. They were trying to get rid of this tattoo right here. You can see it's on their arm. And you can see that 8 months later, that's what they get to. And you can see the process in between. Doesn't look very pretty, right? It's because energy is being deposited and you're getting localized burning inside their skin.
It still doesn't really remove it. Just
Well, so what you see is you see that certain parts of it got removed and other parts of it didn't. So this red actually went away pretty good. It turned to kind of a light pink. Some of this dark didn't, and I'm kind of curious as to why that is. But this person, when you read their blog, was not very happy with the process, but went through it anyway. It faded, but still not completely gone. What they do now is if you guys decide to ever get a tattoo, look for dyes that have been specifically made to be easy to remove later with a laser. They do that now. They have sets of inks, if you want to call them that they use for tattoo parlors that will be easy to remove because they've already been tuned to lasers, so it absorbs the energy and are more easily dissipated.
I heard something that like now because in the like older tattoos, the ink is encased in some sort of gold metal or something like that. But now they're doing more of like a more biological material, so it's easier to break apart. Some of the inks.
Yeah, I'm not sure what their process is. I mean, one, they can tune the color so that it more readily absorbs, and the other, they can just make the pigment more easily degradable once you break into smaller pieces. So that could be part of it. That would make some sense. Okay? So if you ever think about a tattoo, think about what it might take to remove it. Okay? So another thing that you can do is cavitation. So again, these are all processes, and I don't need you to know the specifics of these, but I need you to think about how the laser can affect something in a living body. Right? In this case, what you're doing is you're breaking gallstones or kidney stones. And again, the idea here is if I can deposit enough energy into the object that I'm trying to remove, I can break it up into little pieces. It can cause sort of an explosion, a local explosion. If the pieces are small enough, then I can take them out of my system. Okay? Whether it's a tattoo or it's a kidney stone. Now, this is a dramatization of it over here. It's showing you the inside of a vessel where there was a kidney stone, and it's showing you a laser pulse hit it and broke it up into little pieces. All right? This is also showing you a laser on a large stone. The stone is fragmented to dust with the laser, and then the stone is cleared. Okay? So this is a process that's done underwater because this is something that's done inside, for example, your kidneys, okay, or urethra. You know, different places where there's liquid there, there's water there. So this process has to work there. And the way we tend to get the laser light there is we don't just go, beep, and shoot a really high-powered laser from the outside. We go in with some kind of fiber optic. This is not the fiber optic that's used medically. Those are much smaller. This is a fiber optic used in telephone communications. Okay. Question about that? Okay. So again, another process where I've caused something to happen, I've broken it down. This shows you, have any of you ever had a cavity? Have any of you ever had a laser drill used on your cavities? No? Okay, it's kind of a technique used on small cavities, and it's not used by very many dentists. Some dentists use this technique, but not very many. I remember there was one in Berkeley that was using it 5 years ago. I tried it. I wanted to see what it was like. And basically, the idea is that I can use a laser and I can deposit enough energy. As you can see here, here's a laser hitting the enamel of a tooth, and it's causing a little plasma to be ejected. So basically, it's blasting that tooth. Okay, it's depositing a whole bunch of heat that's causing that enamel to break down and basically vaporize. Okay, now, depending on the amount of power that's deposited, I can either get this kind of an effect on the surface of the tooth, where I remove a nice little circular layer. So if I was trying to fill your cavity, I wanted to remove the bad part, I could go in and shoot pulses of this, and I could be removing layers of your enamel. But if I happen to have the thing cranked up a little too high, or I make the pulse beam too long, and I deposit too much energy, I can have this happen. Okay? I've deposited so much energy that the enamel of the tooth cracks. So the important thing about all these techniques is that you can use a laser to do quite a bit of work, but you have to be very careful of the amount of energy that you deposit. Okay, and over what area. And you have to also know very much the thermal properties of the object that you're making this laser hit. And whether it's in air or water, all of these different things matter. Huh? That's a photomechanical effect. The next one is photoablative. So in this case, you use wavelengths in the 190 to 300 nanometer range, which is what part of the spectrum? UV, ultraviolet. Okay. Our vision starts somewhere around 300 to 400 nanometers is what we can start to see as a really deep violet. So in this case, these laser lights, these photons have so much energy that ends up being higher than the binding energy between molecules. So what does that mean? It means that the energy in this light is enough to make the molecules come apart. Okay? Or ionize. The bond is broken, they separate. Okay? So, the molecular bonds are broken and the tissue components are vaporized without generation of any heat at the edges. It's only obtained with lasers of very energetic wavelengths, UV. The action is superficial because the light of these wavelengths is very strongly absorbed by tissue. Do you guys remember we tried putting a blue LED on a finger? We tried the green laser, here it is, on my finger. Nothing comes through. Well, the blue even less. Okay? It's very strongly absorbed. So they end up using a lot of times a laser at 193 nanometers. And based on the amount of energy that they deposit, they can control the depth of destruction, okay, the depth of ablation, from a few microns to about 150 microns. Okay? So to give you a sense, how thick were your hairs? How much? Nobody knew what their hair thickness was?
60 micrometers.
60 micrometers. Anyone have anything else?
80 micrometers.
80. Okay, so your hairs probably were anywhere between from the 50 to 150, 200 micrometers. Oh, we're getting some people worried over here. Do you guys have thicker hair or thinner hair? So effectively, with a laser like this, we can control the amount of damage to about the thickness of your hair, or less. Okay? Now, why might that matter? Excuse me. Well, let's say we want to reshape your cornea. Okay? So in this case, you're wearing glasses. Okay? Many of you wear glasses. Well, several of you wear glasses. Okay? It's because you can't focus the image at all distances onto the back of your eye. Okay? So we can actually modify your cornea shape so that you have an easier time being able to focus the image on the back of your retina. Okay? How do we do that? Well, we take your eye, we don't take it out, you're just sitting there, you're laying down like this, and first you slice off a piece on top of the cornea. It's called the flap. And you flap it over. Okay? Then you come in with your laser, and the laser isn't really this wide, but that's the area that it's going to affect. And what that laser does is, as it scans, it can control how fast it's pulsing and for how long. It removes a layer of about 10 microns. So it removes like a layer of cells off your cornea. And I have a pattern that I've determined from doing some tests on your eye that tells me the shape exactly of your cornea, and I can figure out where to remove cornea so that I can get your eye to focus on the back of your retina again. Once I've shaped it by removing a layer at a time in a very controlled fashion, I stick the flap back on. And the flap will pretty quickly reattach, and you'll be fine, and you'll be able to see. Now, you guys are young. If you guys have that procedure done, corneal cells can still grow. So your eyes can go bad again over time. Okay? Usually with younger people, what they do is you buy a touch-up plan, which gives you the initial, and then like every couple of years you can go in and do it again until your cornea kind of is slow to grow. Yes?
Are they like completely put you under anesthesia when they're doing this, or how are you
No.
partially awake?
You can be completely awake. There's no nerves there.
Still, wouldn't you kind of, I mean, I think you twitch or something.
You don't see it. You see this part. You see the blade. It's not very well in focus. That's the part that bugs me the most. The laser part doesn't bug me. the part of the knife going across and slicing the cornea, that's the part that kind of irritates me.
And have you actually had to test it?
I haven't. No. Luckily, my eyes are fine. My wife's considering doing it. But I've known people that have done it, and they don't complain of, the only thing that's weird is that, like, you have to kind of lay back for a while after the procedure. Otherwise, that flap will. So you have to kind of lay back and let it kind of stick, and then sometimes they cover your eye for a while, so you have you have your eyelids closed and it's holding that flap, right? And then that thing attaches pretty quickly.
Doesn't it take a while though for your eye to readjust and get like a good again?
Well, your eye is focused by the kind of shaping of the cornea and also the pulling and stretching of the lens, mostly from the cornea. But most of the focusing comes from the cornea. And supposedly, it takes a little while just for you to get used to the fact that, you kind of the muscular movements are a little bit different. But I don't know because I don't have the personal experience, but I've never seen anybody complain about it taking very long. When you first take everything off, it probably takes a little while. You might be teary, and there might be a variety of things happening. So this is showing you on a cow eye the flap removed and the shaping of the cornea. You see how it goes in? That's been shaped. And then they would put the flap back on. And this is like a sideways view of showing you what the laser pulse hits. This is the effective vaporization of a layer of cells. This is the little mushroom cloud from the vaporization of the layer of cells, okay? That's ablation. Ablation, you've just gone poof, and you've made it into its, basically the molecule's been torn apart. Okay? That's the important thing about photoablation. Now, when they first figured this out, they did this with a lot of cow eyes, right? They did this with a lot of cow eyes, sheep eyes, things of that nature. That's how they figured all these things out. But you can imagine when they were first figuring this out, they had to very finely control the pulse length so they could finely control the amount of energy that was delivered into the eye. And it took a lot of experimentation before they felt comfortable doing it on a person. Okay? Now, why do we use an ultraviolet laser to do this? Why don't I use a green laser? Those are cheaper. Yeah, you can see green, right? The reason you can see green is because it goes through. So if I use the green laser, I'd just be poking holes in your retina. Okay? So I use ultraviolet because the cornea, it absorbs ultraviolet energy and blocks it. Okay? It's a natural mechanism to protect our eye, right? Because ultraviolet light, this is the way that it blocks it. But people that are exposed to too much ultraviolet light can get snow blindness, which is the UV. If you absorb enough UV into the cornea, you kind of get a hazing. And that can create other problems with bad vision. Okay, and then the last one I want to talk to you about is photodynamic. Okay, so far we've had mechanical. It causes like a local plasma or a cavitation, some kind of explosion. We've had ablation, which basically ionizes and pulverizes the components. And now we have photodynamic. Photodynamic therapy, PDT, what photodynamic therapy does is it says this. It says, I can take a specific molecule or sets of molecules that can be destroyed by applying the correct light on them. Okay? If I can get those molecules to stick to the thing that I want to destroy, to the cells that I want to kill, then I can use this as a therapy. So if I have a skin cancer, and I can get some kind of agent, some kind of cream, that will selectively stick to the tumor areas, okay, the parts that I want to get rid of. And then I expose light of the correct wavelength to activate those molecules. Once those molecules are activated, they will form free radicals. Those free radicals will destroy whatever molecules are near them. If those happen to be the bad cells that I want to get rid of, I have now destroyed the bad cells. Does that make sense? Yes?
What about the place to show the good cells around it too?
If it's attached to good cells, yes. So the trick here is to find a substance, a chemical substance, that is both activated by a specific wavelength of light, or a range of wavelengths of light, and selectively binds the bad stuff. Okay, that's the trick. If you can figure that out, then you're fine. This technique works well. Now, they have creams. A lot of my friends that are a bit more on in years have been exposed to a lot of sun, and they have a lot of what they call precancerous lesions. And Jim went through this process. What they do is they give you a cream, and this cream basically tends to select more strongly adhere to the parts that are these precancerous lesions. It adheres to all of your skin, but more strongly the parts that are bad. And then you kind of just walk out into the sun for a very controlled amount of time, and that destroys, it activates this chemical, and it destroys those precancerous cells and some of the healthy stuff. And so you get a nice kind of red splotchy appearance for a while, but you've selectively destroyed more of the precancerous cell layers than you have of the healthy cell layers. And then the healthy cell layers regrow, and the cancerous ones are gone, precancerous ones are gone. Okay. We also have researchers in Canada that are part of the Biophotonics Center that will go in and remove cancers this way. So they can do it both for topical cancers, but you can also do it for something inside if you open up and you have selective binding, and then you can expose the light. These kinds of techniques can also be used for removing certain types of spots. There's different ways. There's one of just laser cauterization, but there's also ways with chemically activated agents, okay, depending on what it is that you're trying to go after. Okay? So, this is showing an example. I've got my tumor in here. This part right here is the tumor. I'm lucky because I can get these little tiny yellow drugs, and this is false color. I can get these little tiny drug molecules to stick to my tumor. I turn on the light that activates those molecules, and boom, all those cells are destroyed. And the tumor mass is destroyed. Okay? The good thing about this is if I can have something that's selective, that isn't sticking here, but is only sticking to the parts that I want to get rid of, I can get rid of very small clusters, beginnings of cancers, beginnings of tumors. A few cells, maybe, which I would never, ever see in any other way. But because this stuff sticks to it selectively and I can irradiate a large area, boom, I've cleaned up the cancer in that area. Okay? The trick again is finding the drug that sticks only to the bad stuff. That's the trick here. Okay, so with that said, you've now seen these 4 different effects that can happen with laser light. The thermal effects were used for what kind of common use? You guys remember any? We used a laser to deposit heat to destroy. Hair removal. Yeah, that was the hair removal. We deposited the energy into the follicle of the cell. That caused heating, but not heating to the point of explosions or heating to the point of plasmas. No, it just heated it. 100 degrees centigrade, desiccated the cells, denatured the proteins, boom, that hair cell is gone. Okay? That was the thermal effect. Mechanical effects. What have we seen that could be mechanical effects? What's another example of that? Cavity, so removing layers of enamel. What else? Tattoo removal. Okay, gallstone removal, those types of things where you're causing a local explosion that's causing the shattering of pieces. Photoablative. What's our favorite photoablative example? Laser eye surgery, LASIKs. And photodynamic effects, we've got this drug uptake, selective drug uptake, which then is activated by light. That drug, when it's activated, forms free radicals. Those free radicals destroy the cells around them. Yes?
How would you get a drug to stick only to certain cells and not the others?
Well, that's the magic, right? I mean, this is the part that's difficult. What you could do is you may have a situation where you can have a photoactivatable molecule that's attached to something that has a structure that fits inside of proteins that might be found on the surface of the tumor, or that might have a preference electrostatic interaction. So the positive and minuses are laid out in such a way that you can have a favorable contact, more favorable than with most other proteins in healthy cells. You may have something that you try to get absorbed by the cell and taken in because it recognizes something. It thinks that it's another nutrient that it wants or something that it needs that is more taken up by a cancer cell that's more active than by a healthy cell that's less active.
When you say more, does that mean like some of the healthy cells will still?
Yeah. Yeah, you pretty much with PDT, you're always going to get some collateral damage. But I don't know if you guys have ever thought about this, but every single cancer treatment we have has collateral damage, has extra damage. The question is how much? Okay, PDT is trying to minimize that. Things like chemotherapy just say, boom, blast it all. Okay, radiation is, again, it tries to be more selective, but it depends. Again, you get collateral damage. All of these techniques have that. Okay, so let's move on to biophotonics tools. So, the biophotonics tools that we're going to be covering are going to be quickly the laser, because you guys have now been hearing a lot about the laser. We're going to talk about fiber optics. So, the laser provides powerful, controllable photons to manipulate, alter, and probe biological samples. Fiber optics allows you to bring light anywhere, pretty much anywhere. The microscopes lets us see living things at a very small scale. The eye, we're going to talk about because it's a tool that we all know and love, and it's a great example of a biophotonics tool. And then we're going to talk about the CCD, which is a tool that we use a lot because it can gather light and tell us something about that light. Okay? And then we're going to leave this one to after next week, which is the spectrophotometer, and that allows us to get specific energy and intensity information for light. Okay? And you guys have done a version of the spectrophotometer with the paper spectroscope, but you will be, after next week, and after we do our tour of CBST, then you'll be doing some things with the higher end spectrophotometers. Okay, the laser. As we saw a week and a half ago or so, laser stands for light amplification through stimulated emission of radiation. The big deal with lasers, monochromatic, which means what? Single wavelength is an easy way to think about it. Coherent. Coherent is a little bit of a more difficult concept to think about, but it basically means that if I find the one wave in the laser beam, I know about all the other waves in the laser beam. I can figure out where all of them are and what their relationships are to each other. Okay, in sunlight, the waves are all scattered, going in all different directions, doing all their own thing. And just by finding one, you really have no idea of what the others are doing. In a laser, if I know where one is and what its phase is and its speed, everything, I will know what's happening to the others. Okay, in that beam. Directional, we see that I can point a laser. It's very directional, travels one way. When we had an incandescent light, the light goes everywhere. Right? The sunlight goes everywhere. It can focus to a few hundred nanometers, which means I can concentrate at really high energy density. I can pack a lot of photons in a small area. I can range it from ultraviolet to visible to infrared, and some are tunable. And I can pulse it down to very, very short pulse lengths, which again allows me to control not only the amount of time, but also the amount of energy that I deposit. And you guys remember we talked about how it worked in a ruby laser? I know I start to see, the windows are closed, but I start to see these things moving. It's a little bit, they might not be perfect seals. Anyway, how does the ruby laser work? Remember, the big thing about this was you needed to have an external source of energy that was constantly flashing and putting energy in, which was being absorbed by the atoms. The atoms basically dealt with the fact that when they were excited and then released energy, they could then, that release of energy, that photon that's released, could excite another atom, or could, if I found another atom that was already excited by the flash tube, then two of them could go out together, and then you could get this multiplicative effect, where they're joined by two friends, and then another set of two, and another two, and another two, and it just keeps going, okay? And because you use these mirrors, and because you have a selective space of this and of the rod, you only pick the light that's going parallel within that. And when you have enough of them lasing, that means they're excited and exciting others, that you have a beam that escapes and it's directional, and it's coherent, all of these different things. Okay? Lasers come in many colors. This is from a conference I was at a couple years ago, actually the same conference I'll be at on Monday, called SPIE. It's a Society for Photonics Industry and Engineers or something like that, or International Engineers. I always forget. But basically, what may be hard for you to envision is somewhere in the order of 30 to 40,000 photonics aficionados come together. And this is only one of the meetings they have during the year, but this is one of their big ones for Photonics West, it's called. And there's 2 days, there's a Saturday and Sunday, this coming Saturday and Sunday, where they just talk about biological applications. And then there's a Monday, Tuesday, Wednesday, Thursday, where they talk about telecommunications and all the other applications of photonics and new types of microscopes, all kinds of things. There's on the order of close to somewhere 500-600 vendors that come from all over the world to show off their wares. So this shows you that they will sell you a laser of any kind of wavelength. What they're doing here is this is the laser, and it's shining a beam onto a ping pong ball. That's how they show you for display purposes the different colors. Huge industry, believe it or not. You just recently saw this, so we don't need to go over this again, but the laser can act as a hammer, and it can break things. The laser can act as a cutter, cauterizer, remove layers. It can cause molecules to ionize, as we just discussed. And the laser can actually make cells or tiny beads move. So this is a movie where what they've done is they've taken different laser beams and they are able to focus them through lenses onto small beads in this case, but these could be cells, it doesn't really matter. And you can use the laser as a tractor beam. You can make the laser effectively trap something, and you can control how it moves. Okay, so this is 6 of these things here. I'll play it one more time. And it's taking these beads, and it's making them, they're moving them up and down. So sometimes these things are called laser scalpels, or laser positioners, or laser traps. Lots of different names for these things. But you might ask, why do we care about trapping little beads or trapping cells? Well, what we can do with that is we can then study them. So have you guys ever looked under the microscope or like blood cells? Things are moving around. You ever looked at pond water? Little organisms are flying all over the place. It's hard to keep them still. Okay. Well, now you got the laser beam. The laser beam goes and grabs it. Boom. Okay. Now all of a sudden, I can grab that cell. It's harder to grab an organism. I can't quite grab an organism. They don't like it. They tend to. It's a little too much energy focus. It's not very fun for them. But when I grab a cell, I don't have to use as much energy. I can focus my beam down to about a micron. I can grab a cell. Now, I've grabbed that cell. And we do this all the time. This is happening right now at Oak Park, and you guys will be seeing the instruments that do this. But I've grabbed that cell, and now I can investigate that cell. I can shine specific colors of light on that cell, and I can see how it responds. So why might that matter? Well, what might you do with that? What could you tell? What might you care about a cell, finding out about a cell that you've trapped? You guys think of anything? I know it's a bit of a tough question. Do you guys think there's any difference between a healthy cell?
Well, earlier, I think it was the other guy who was talking about watching cells get live cells.
So you might want to watch a process that's happening in a cell, and you might want to hold it still, is what you're saying. Okay? That's definitely reasonable. Yeah, think of it this way. So you've got a healthy cell and you've got a cancerous cell. Might there be a difference between those two cells? It's possible, right? And a lot of what we do is trying to figure out what that difference is. So cancerous cells tend to be on the go. They're constantly trying to multiply. They're very active. Being very active, what does that mean in terms of what's happening inside the cell? It means that there's a lot of generation of DNA. There's a lot of extra energy in that cell. Okay? Those molecules have specific signatures in terms of optical signatures, the way they react to light of specific colors. Okay? They have specific things that they do. Because of that, I can grab that cell and I can do something. The most common thing that we do at CBST is we do Raman spectroscopy. It's a type of spectroscopy that looks for vibrational modes within atoms, aggregate vibrational modes. Okay? I know that sounds strange, but if I have a lot more DNA, I will have a stronger signal that shows me the vibrations that are normal for DNA. If I have a lot more NADH, I will have that signature will be enhanced compared to a healthy cell. So what I can do is I can trap the cell and do this type of investigation on it. The other thing that we can do is we can trap a cell and we can do not even microsurgery, incredibly small surgery. I can take out a mitochondria in the cell. I can use one laser to hold my cell, and I can use another laser to selectively blast just a small part of that cell and see what the cell does, so I can learn more about how cells function. Okay? It's called laser surgery. Okay? Laser cell surgery, actually. We had a researcher that was doing that as well. So there's a lot of different things you can do when you can trap it. Now, I can't trap you with a laser beam. Okay? That doesn't work. The amount of energy that I would need for that is ridiculously large. Okay? But I can trap a very small, 5, 10 micron bead, okay, in a solution. Now, the thing that I was telling you before about the cancerous versus non-cancerous cells, let's say that someone that you know and love develops some kind of lymphatic cancer, or a cancer that we now have to replace their bone marrow. Okay? What we do now is we take their bone marrow, we irradiate them to make sure that all remaining bone marrow is dead, and then we take a donor's bone marrow and put it inside that person. That person may have a rejection. Very likely some kind of rejection will happen. What we'd rather do is take not your bone marrow, but the person who's not healthy, take their bone marrow, and we'd rather separate the healthy cells from the cancerous cells. Okay, that's the dream. And the way we can do that is by flowing a whole bunch of these cells through a system and selectively grabbing a cell at a time, investigating and seeing if it's healthy or not healthy, and binning it, putting it on the side of the healthy cells or on the side of the unhealthy cells. And you do this for long enough, you get a population of healthy cells that are from the patient that I can feed back into the patient, and hopefully that will lead to them generating more and more and more, and they'll get better. And they won't have any of the rejection issues. Okay? But if I can't grab a cell, I can't query it. I can't figure out what's going on with it. Because the other ways that I have of querying whether it's cancerous or non-cancerous involve me like staining the cell. But if I stain the cell's dead. So I want to keep the cell alive. I want to query it, find out what the deal is with that cell, and then put it in the right bin. Okay? So that's a technique they're working on. The problem right now is it does one cell every minute. Too slow. Okay? We need to do this for millions of cells. You can't wait 5 years for your cells to be sorted. Do you have a question?
With bone marrow, doesn't it have to be almost like identical? It's not like blood where it's the same kind of...
Yeah, that's the problem, right? Chances of you getting the same thing. I mean, if you have, an identical twin, you're in great shape, right? But we don't all have identical twins. So maybe someday we will. Who knows? With all the genetic engineering. But the question is there, what can you do? So this is one technique that they've looked at. So this is a diagram showing you a more complex setup, and it shows you a multiple laser trap setup. And what they can do with that, laser tweezers, so what you see here is, here's a laser, here's a microscope objective, okay? And what they're showing you is that they can go in with the laser, pass it through some things, pass it through some other splitters and joiners. The yellow and blue lasers are joined to do the screen, and then there's a red laser here. They can use the different colors lasers to trap things or to cause a different motion in the object. And this is a red blood cell, which are kind of donut-shaped like. They don't have a hole in the middle, but they kind of have an indentation. And what you can actually do is they can manipulate and rotate that cell. So by the use of multiple lasers and the way they impart momentum on the object, they can suspend that cell and control its orientation, just using the lasers. And this is the single cell laser surgery. This is a yellow fluorescent protein transfected mitochondria in a live BCE cell. I don't remember what the BCE cell is. I think, yeah, I don't remember what it is anymore. But what it's showing here is that they've labeled the mitochondria in this live cell with yellow fluorescent protein. So whenever they shine higher energy light on it, it glows back yellow in this case. It's not green fluorescent, but yellow fluorescent protein. And they're showing you that they can selectively apply a laser pulse to remove just one mitochondrion. This is what it was before. They do the blast, and this is what it looks like afterwards. So they can selectively control that laser beam and the amount of energy that it didn't kill the whole cell. It didn't kill a whole bunch. It just removed one mitochondrion. And the idea here was that someday we may want to actually have robotic systems that can do surgery on a cellular level. Okay? Again, pretty far off in the future kind of idea, but it was something to show that it could be done. Okay, so let's move on to the next element here, next tool. And this is the optical fiber. So, optical fiber. Optical fiber traditionally is made up of strands of optically pure glass or now certain plastics. The idea is that it's used for transmitting light for telecommunications, for your internet, for medical imaging, all kinds of different things. And the idea is based on total internal reflection. And what that means is here that I can shine light into a fiber. Think of this middle part here, the core, as the glass part. The cladding is just the plastic that goes around it. Okay, it can be made of different materials, the cladding. And no matter if I've got a laser that's coming in like this, at this angle, or at this angle, they will all be accepted into there, and they will bounce into that glass fiber until they come out the other end. Okay? Now, so what? I could have just shot it straight. Well, you want these fibers to curve. You want them to go all over the place. You want them to go from here to the other side of campus, and they have to go and make turns, and they have to go and get kinked and go up and then come down. And you want the light to continue traveling through there. Well, the beauty of these fibers is that it doesn't matter if you bend them. The light still travels through them, still bounces, and comes out the other end. And I know this is a little bit hard to see, but in this tube here, you see the red laser beam goes like that, like that, like that, and then comes back out. Okay? This is a straight version of it. I don't have, the bent one disappeared. But I've got my laser. Of course I can go straight through, right? But I can also do all kinds of other things, right? I can bend it. You can see it comes out the other end. It comes up on top now, depending on what my angle is. But it still travels through the tube. Okay? You guys see that? Now, I don't know if you noticed, but you do lose a little bit. I can go at a steeper angle. You do lose a little bit here and there on the edges. Some can escape. And that's usually what the cladding is for. The cladding helps to minimize that. Okay? Now, this is our fiber optic that we're going to test in here. Let's have somebody back there grab this. You can look at the, feel free to look at it right now as we measure. You can see if you see any kind of little bits of glass in there. Yeah, all this mess. Okay? Well, it doesn't matter. You guys see lots of knots, problems all over the place there? Well, don't look straight into them right now because I'm going to shine a laser into them. Now point them down at paper and tell me if you see a green dot. See it? Okay? So I'm pulsing this on this end. It's going through this mess of knots and all kinds of other things, and it comes out that end. Still working? Okay? You see, I shine it into this end, and it comes out the other end. Okay? So I've managed to send light from here to there. It's bending, it's doing all kinds of things, but it's still usable over there. Okay? So this is how we pass your phone communications. This is how we pass your internet communications. Okay? All that stuff is, you're welcome to. Here, I'll pass this around. You guys can look at a small version. Okay? This is how all of that happens. This is actually fiber optic cable from the telecommunications industry. And it can pass light for miles this way. And then they have a little box that kind of takes the signal coming in, amplifies it, sends it back out, and they can go for another umpteen miles. And this is how they can pass a signal across the ocean floor.
Now with the thousands of telephone and internet signals that we go, how do you discern between one call and another call, all these different ways bouncing down this cable?
Excellent question. What am I hearing here? Sorry. This thing is talking to me. I think I have a person lecturing. Okay, sorry about that. One second here. Okay, so how do you pass multiple signals over that? What are some ideas? What do you guys think? If I wanted to pass a whole bunch of different signals in the same little fiber. I could use different colors. So your conversation could be 535 nanometers. Your conversation could be 600 nanometers. Okay?
You put it in a frequency.
Okay, what does that mean?
Well,
You don't want me to put you on the spot, but in your
there's like a regular frequency that it sends, and then you can like superimpose like information onto it, like make it higher, lower, and then you can put like a bunch of on, and you have like a computer that just learns all the information that's inside, and then you can overlay like a whole bunch of stuff on it.
So, what do you guys remember that's special about lasers? Laser pulses. What did we talk about with laser pulses? Monochromatic. What else? Coherent. What else? Directional, but in this case, I'm going all over the place anyway. You can make them super short. Okay. So, I can turn on and off a laser incredibly fast. Okay? Imagine I can turn a laser on and off basically 100 million times a second, maybe 1 billion times a second. Okay? So at that rate, I can say that the information from pulse 5 to 500 is your conversation. 501 to 605 is yours. 605 to 800 is your piece of information. And I've now taken 1 billion bits of that information that I can send, and I've chunked it. Okay? So that I can send maybe 1,000 different bits of conversation per second to my other location. Now at the other end, I better have something that's pretty good about figuring out which bits are which. Otherwise, your conversation's going to get mixed with your conversation, and going to mix with your conversation. It's going to be a mess. I don't know if sometimes you've been on the phone and you've heard other people's conversations. It can happen. They used to happen because of electrical crossing. Now it can happen because of optical crossing. Yeah.
So how do they take audio and transform that into a coded light signal?
So this is all something that we're going to be talking about a little later called digitization. Digitization is the process by which I take something that is analog in nature, something that has infinite variability, like your voice, and I make it into discrete chunks of mathematical information that I can easily pass through a machine. Okay? And we can do this with video, we can do this with audio, we can do this with email, anything, any kind of digital information we can do this with. But that's how those fibers work. They use multiple frequencies, they use multiple fibers, multiple frequency of laser light, so different colors. They use this ultra-high speed of transmission. All that stuff can travel together in that same optical cable. And now they've just come up with ways of packing 10 times more into the cable by changing the properties of the cable. Okay, so they're actually replacing the cable that goes between here and Europe to give us 10 times higher density of data transmission. Okay, so pretty much somewhere along the chain, whenever you're using your phone, you're doing your email, you're looking at a YouTube video, there's been fiber optics somewhere along the way. Okay, so and what you can also what you're also not seeing in that, because that's a single bundle, you can also make in one wire, you can pack 100 bundles. You can make really, really, really tiny fibers that are all stuck together. Okay? And when you do that, each one of them can carry, again, you know, 1 billion bits of information per second.
Well, wouldn't that lead to more of the crossover thing because there's not the padding around each single one?
Well, that depends on, you could have a little tiny layer of cladding anyway, okay, very small, just a different material. Or, depending on if you've got straighter runs and you don't have as much bending, then you won't run into that problem. Okay? So, lots of different things you can do with this. Oh, this is, I had a little video of that. I forgot it was a video. But it doesn't matter. You already saw the basic idea. So, what can we do with a fiber optic? Well, you can imagine that if I can make this fiber optic really small and I can put it inside your body, I can bring laser light to any part of your body that I would like. Pretty much. Okay? So, one thing that was done is they made laser-activated shape memory polymers for microdevices. So what this means is I can get a laser to, this is, see this cable right here? This is the fiber optic right here. And this is a little piece of shape memory polymer on there. When I pass the light through my little cable and it hits this shape memory polymer, it opens, makes a little funnel. Okay? Or it makes a little flowerette like this. And this is the size that we're looking at, this device being, okay? Really tiny. Now you might say, okay, so that's kind of weird. Well, let's say that you have a stroke. And a stroke is basically, anyone know what a stroke is?
Artery clogged and blood is not moving to a section of the brain.
So right, your heart beats right, it sends blood up the arteries. Let's say that one of those things gets clogged. You got a bad plug there, okay? All those chips that you've been eating all those years and all the fatty food has finally come back to haunt you. And a big clot goes up and blocks it. Now all of a sudden blood can't get through. Problem, right? We know that living tissues, if they don't get their oxygen, their fresh oxygen, they're in trouble. Okay? And that travels through the blood. So we need to somehow get rid of that clot. So what can we potentially do? We can come in, make a cut in your big artery here in your leg, snake through, go through, push that fiber optic through your arteries. Tiny, tiny little thing, 1 millimeter in size. Push it through, snake it around. Oh, I got to make a bend over there, bifurcation, okay. I get to the clot. I push this whole assembly through the clot, because the clot is hard, but it's not totally hard, right? It's not like rock solid hard. It's not a rock that's in there. It's this mushy, fatty, different materials that have been stuck together, and dead cell parts, things of this nature, cell walls and things. I push it through. I turn on the laser. The laser heats up the shape memory polymer because it has a memory. When I heat it back up, it remembers what shape it should be, becomes a little umbrella, and now I take it and I pull out your clot. And all of a sudden, boom, pressure is restored. You got blood going through there again. And if I can do that fast enough, the stroke doesn't lead to any permanent damage. Okay? Question? Yes?
How do you tell when you're through the clot?
Well, what they do here is they do a very, very low energy X-ray, like a continuous imaging. And that's also how they know how to snake, where to snake through. So they can see the clot because they put a dye into the blood, and wherever the blood isn't flowing, it goes dark. You can't see there. So they can see it. It goes up to here, and it should be going further, and it doesn't. So they can push that through and then pull it out. Yeah?
Isn't stroke usually like in the arteries in the brain?
Yes.
And if you put it through the femoral line, you have to go through the heart.
You sometimes can have to go through the heart.
Can you do this for preventive? Like if you see those going through a clot, they're out of there now.
Well, so there's a question even before that. So the question was, can you do this for preventive? Well, can you even do this at all in the hospital right now? Okay. This was a technique that when we first started the center, they were working on really hard. And it turned out that there were a couple of competing techniques. One technique was you deliver a laser and you blast it. That's one technique. Another technique was you deliver sound and you make an intense sound wave that creates pressure that then breaks apart the cloth. That was another technique. This was one technique. So all these techniques were competing, vying for attention, vying for venture capitalist money. Okay, they were all going at things together. And this one, can you think of any problems that might arise with this?
Takes too long.
Takes too long? That one's not too bad. Well, the good news is when you're going up an artery like this, it goes from large to narrower. So the way you're traveling through the system is you're trying to travel in a direction where you would never be in a situation when you're pulling it back through something narrower. You're hoping that pretty much you've got that relatively contained. Or if you are going through something slightly narrow, it's very minimal. But can you imagine, so I've got a bifurcation, here's my big artery and it splits into two and my clot's over here. And I punch through it, I grabbed it, I'm pulling it back. Now imagine the blood is still pumping, right? There's a lot of pressure going this way, right? A lot of pressure. But there's no pressure here because there's been no flow. I pull it back. What happens at this bifurcation? It might slip off and go up this one. No, it'll just create the stroke over there now. Well, this is already there. So it's blocking oxygen to your brain, but now you got a problem over here. Now, what about if you punch through and it breaks? Now you just created the problem further upstream. Now you created 2, 3, 4, 5 problems upstream. Okay? So the idea with the other techniques was blast the heck out of this thing, the clot, so it's so small that you are effectively causing tiny little strokes, but nothing that will affect in a large scale. But really, really small, tiny little blockages that eventually will clear out. Okay? That was one idea. So this technique, they tried making a wire that snakes through, so like you punch it through, and then you activate it, and it kind of becomes a spiral, and it grabs the clot. So they've tried a lot of different techniques. Long story short, they've only done this with cows. Okay? It hasn't been used with humans yet.
Have they actually done it successfully?
With cows? Well, they take dead pieces of artery and they mimic a clot. It's kind of like, when I remember this work, that's where they were. That's what they were doing. Now, I don't know what happened to the other techniques. But these are very important procedures because stroke disable and kill a huge number of people every year. So it is a very hot problem. It's a very important problem. But just to show you that, this is another way that you can use fiber optics and lasers to try to get at this problem. And then there was we had another graduate student. And this graduate student, this is going to sound kind of weird, but what they were doing is they were taking 10,000 little strands, little glass strands, putting them together. They were each 4 micrometers, so much smaller than your hair, okay? A 10th or a 20th the size of your hair. She was sticking 10,000 of these together, polishing them in such a way that she would create a 500 micrometer, actually, diameter image guide. So a 0.5 millimeter cable, okay? 0.5 millimeter. So half the thickness of your fingernail. That thing would have 10,000 of these in it. Okay? And you can imagine that the light that goes into one will come out the other end, right? So this is her looking at a resolution chart. She could look at something. She could put a little microscope at one end of this thing and put the other thing on something really small, and she could see through it. The light would travel. So it's like an imaging guide. You have 10,000 pixels of an image. It's like a 10,000 pixel image. And then she was putting little micro dots that were dumped there by an inkjet. So she'd have this little 10,000 fiber bundle. She'd use an inkjet printer to deliver little tiny drops. Okay? onto the end. And in the end, it would look like this. So this is the 500 micrometer fiber right here, right? With all those tiny little 10,000 fibers in there, okay? Then she'd put these dots like this. And this is looking at one dot. See, it acts kind of like a lens, and it's showing you the fibers, the individual fibers of the 10,000 fibers. And she would put some chemistry into these things. Now, why was she doing that? Well, she wanted to study gum disease. She wanted to get a sensor for gum disease. How many of you guys have gone to the dentist and they take this little metal probe and they stick it between your teeth and gums? You guys ever had that happen to you? And they say things like 2, 3, 1, 5, 3, 2. And they go 6, ooh, 6, oh, 8, oh no, that's a problem. That's measuring the depth that they can go in with that sharp metal tip between your gum and your tooth, right? And why are they measuring that? They're measuring that because as you get older or you start developing gum disease, that distance increases. So effectively, your gum is detaching itself from the tooth, which you do that long enough, and your tooth pops out. Okay? I worked as a dental assistant when I was your age in Italy, and actually saw people that came in and had such bad gum disease that they would open their mouth and say, "Oh, my tooth is hurting, my tooth is hurting." The dentist would come in there, they'd open their mouth, and they say, "This one? Oh, yeah, I feel much better." Okay? These were 80-year-old patients, okay? Fortunately, they weren't, 20-year-old patients or 18-year-old patients. But gum disease is a problem. And ideally, what you're trying to do is figure out gum disease earlier, at earlier stages, so you can figure out ways to treat it. So what she was making is, you see this thing right here? That's that pointy thing that you stick in there, the metal thing. What she wanted to do is, instead of having that be a metal tip, she wanted to put the fiber optic bundle there with the 10,000 little fibers in that tiny little thing, so that when it's poked in there, she can put some special detectors here that will react if there are products there in your gums that are likely to be precursors to gum disease. So it's kind of like it's like an early warning system. She wanted to poke it in there and see if there's early signs of gum disease. She would have the right enzymes that would cause a reaction, which would then fluoresce. So she would come into the fiber, she would shine blue light down, and she would look and see if one of these lights up, because a reaction has happened and now fluorescence would occur there. And this is dropping. So this is just showing you what she would see. So this is if you just use light, and this is what she would see if the dot was activated. She would shine blue light in, she'd look at the green light coming back, and if she saw it, she'd know that that particular dot was activated with that particular enzyme. So the idea here was that you could have these 7 or 8 dots, or more dots eventually, that you stick in there, they activate if the product is there that you're looking for, and now you know, instead of having to go and measure that all the time, you just know if there's early signs of gum disease. Questions about this? So what you see here combined is a fiber optic, a whole bunch of fiber optics. You see fluorescence and imaging, all combined together. Okay? And this was the first enzyme-based, enzymed fiber-based sensor. Okay? So she did prove that this could work. It isn't in widespread use again, because something that you guys might not have readily present in your mind is that when you have a great scientific discovery, or you make a really practical instrument, you show that that it can be done. It doesn't mean that it will be done. There's costs, there's whether companies will be put together, there's whether you find financing, there's whether the market is right, there's all kinds of other factors. Okay, why don't we take a 5-minute break? And what you're going to do is you're going to physically write on these, okay, and make comments. And then these are going to go back to the people so they can read their comments and update their report. They're going to get your comments, they're going to get our comments, okay? And then you'll have a chance the people will have a chance to incorporate all these comments.
Is the grade going to be based on the revised draft?
The grade is based on your first draft, the comments that you give your peers, and the final draft. Okay? And traditionally what's happened is the first two parts constitute about half the grade, and the final constitutes about half the grade.
So we write our name along with our comments, they know who gave them?
No, that's the whole idea of anonymous peer review. Okay? Because the idea is you're going to be brutally honest. Okay? And they're not going to know who did it. Okay? This is how it works. When I submit a paper, any of our scientists submit a paper, they pick 2, 3, 4 people out there that would know about the kind of work that I submitted, and those people let you have it. Okay? Doesn't mean they're mean. I mean, sometimes they're mean, but it doesn't mean they have to be mean. I mean, some people are very nice and civil about it, okay? But that's the idea. You're trying to get them to realize where they can improve. And things that you have for looking at that are, remember that checklist that I gave you? And remember the handout that I gave you with the information? And also you can comment on their graphs. You have some information about graphs too. Okay? So make sure you write it legibly, because I have to grade your comments to other people. Okay? What we're going to do when this is due is I'm going to take your whole packet, I'm going to scan it, and then we're going to separate them out. So I'm going to know which comments you made. Okay? That's why I don't need your name. I'll know by the sheer numbers that you have who you were. Because if you have 13, 14, 15, you were 12. Okay? Question? Okay.
So bring the revised copies back on Wednesday next week.
I'm trying to remember if it's Wednesday or Monday. I'll check that at the end. Okay, I can go back to my spreadsheet and check. I think you have at least a week for doing the revisions now. I mean, for doing the commenting now. Okay? Now, you can be... The idea by looking at other people's papers is that you'll see things that you might have forgotten or missed that you'll want to change and improve in yours. Okay? And remember, the idea is that whoever's reading these reports should be able to duplicate what they did and get very similar results. Okay? If the information isn't complete, then something's missing, and you need to point that out to them. Okay, any questions about this part? Again, make sure you write. Ideally, if you do it in pencil, do it pretty dark, because I have to scan these and then I have to grade based on the scans, and it's hard to, sometimes it's really hard to see really light pencil. It doesn't scan well. So just do your best, please. If you can use a pen or just a darker pencil. Yes?
If we get feedback from you, for the what you sent it to you.
We are going through those right now during the same time that you're doing this. So when you get your peer review, you'll also get our review.
Okay.
So you'll get it will be your 4th peer. Okay? Though you might give our stuff a little bit more weight. It just depends. Because we're the ones grading it. Okay? Any other questions? Okay. Let's move on to the microscope. How many of you guys have used a microscope sometime in your life? Raise your hands. Yay, good. That's a good thing. Okay, so microscope. I'm not going to go through the long story here, but basically it's been around for a while. We're talking now about 400 plus years that it's been around. And here's what one of the first versions looked like. A nail and a hole and a lens. Okay? That's one of the first microscopes. And here's, not too much later, it turned into this, with an objective here, a set of lenses here, and a mirror here to get the light into the sample. Probably some of you may have even used microscopes that looked just like this or very similar to this. I know I did, and this is like a 300-year-old model kind of thing. They've gotten better, and I'll be showing you one in a second. But just to show you that there's been continuous progress. And basically, when you look at the progress in microscopy, what you see is the new techniques being created. Okay, that's the main thing that you see over time. And what do the new techniques do? They allow you to see things better. They create contrast. Pretty much in microscopy, what you're trying to do is you're trying to see something well. So the push has been to seeing things that are smaller and smaller, while still alive, because that's the beauty of optical microscopy. You can see things alive. And the other has been to get contrast somehow, to get information about the thing that you're looking at. Okay, structural details. Okay, that's been where things have gone. Your standard optical microscope when you go to the lab, ends up looking something like this. It has your eyepiece, it has your objective, it has your specimen tray, it has your condenser, and it has your light source. Effectively, this light is focused by the condenser onto the sample. The light that goes then through the sample is focused by an objective, which then is magnified further by an eyepiece. And sometimes this eyepiece is a camera, in this case, so that you can get a digital image. Okay? Relatively straightforward. So now we're going to look at a microscope here. And this is what we call our QX5. And what I'm going to do, I'm going to show you this microscope. The beauty of this microscope is that it doesn't have an eyepiece. It has a little CCD. It has a basically digital camera. Okay? It has 3 magnifications, 10, 60, and 200. It has a light source, and it has a lens. Okay? So I can take this, and I can see how good my shave was this morning. Okay? I can look at the weave of my sweater. Okay? I can look at all kinds of things. But the thing I wanted to show you is I have a sticky here. And if I look at the sticky, this is from light coming from the top. Okay? So this is what's called reflection microscopy. I'm shining light on the subject, light's bouncing back through, and I see it. I can also shine light from through, or transmission. This is the most common type of microscopy that you guys are used to, where you shine light through the sample to see what's going on. And what you'll notice is that it tends to emphasize slightly different things. Things look a little bit different, whether you light them from the top or you light them through. Okay, so those are 2 different types of microscopy. Just to show you something here, I have a picture from a menu of a nice pasta dish here. Okay, this is a color brochure, just to show you how this is generated. There's my picture. You see there's a little bit of green onion in there, a little bit of tomato, and the pasta noodles. Now, you see color, right? Well, and the way the color is produced in magazines is through dots. So each dot is not an individual color, but these are, what color dots do you see? Yellow, red. They end up being cyan, magenta, yellow, and black. Okay, because I can recreate all the colors in inks by combining those 3 colors and 1 black ink. Okay, so the size of the dot, the separation of the dots, again, gives the impression of color. Okay, and I can go even higher magnification. And it doesn't get super sharp, but that's about what you see. And it's clear on the computer. You can see the different colors of dots a little bit better. But this is how all your magazines are done. All your color printing is done. This is how your inkjet printer works, okay? By combining these different colors. And the microscope, by varying magnification, allows me to get closer or farther away from my sample. And it allows me to investigate what's going on and see it. And again, I can do light from different directions and see different things. Okay? So, what are some other ways that I get contrast? I can get contrast through something called polarization. So here's your basic microscopy setup. I have light coming through. I have my condenser. I have my specimen. I have my objective. And I have my eyepiece. Well, what I can do in here is I can stick in 2 polarizing filters. How many of you have ever owned polarizing sunglasses? Okay. What do polarizing sunglasses do? They cut half the light, okay. But I could do that with just a gray lens too. They cut out glare. So what they do, they act kind of like a gate, okay? If you can imagine, if light beams are traveling like this, and another set of light beams are traveling sideways, I can selectively allow only the beams that are coming in with a certain orientation to come through. Okay. And the thing about glare is that whenever light from the sun, which is going in all directions, hits a surface and bounces, it's always polarized perpendicular to the surface it bounced off of. So as it hits the road and comes back, or hits that puddle in front of me and comes back, it has a fixed polarization. Sunglasses are made so that they block out that bouncing light, but keep the rest. So therefore the glare gets reduced. Okay? So this polarization idea, if I have two polarized sunglasses and I put them like this to each other, you'll see black. If I put them like this to each other, you'll see gray. You can see through it. Okay? You'll see black. And the basic idea is I can use this in microscopy. I can put, effectively, it's like putting one of my sunglasses, polarizing sunglasses here, and one up here, and I can put them at 90 degrees to each other. And what I'll see is I'll see something like this. If I use a hair, and I'll see something like this with sugar. So, in this case, I'm looking at a sugar crystal through a microscopy technique called dark field. Dark field is just, instead of having the light come through my subject, I'm going to shine the light from the sides of my object, and I'm going to see what light bounces back up into my eye, to my eyepiece. Okay? Bright field was the one we saw with the light from beneath. Reflection is the light from the top. Dark field is the light from the sides. Notice this is a hair in air. On the air part, light coming from the side doesn't go anywhere. But when it hits the hair, it comes up. So I see the hair, but the rest is a dark field. Bright field, this would look bright, and this would look darker. That would be bright field microscopy. This is dark field microscopy. This is polarized microscopy because what it does is it says, by having these filters in there that polarize the light, in theory, nothing should be coming through. I've got them crossed to each other. There should be no light coming through. But the reason I see some is because the biological material that I have in the way, in the path, is birefringent, which means it turns light. Traditionally, materials that turn light are materials that are very highly structured. Hair is very highly structured, and it's birefringent. It bends light. So it allows you to do this. Sugar crystals do the same thing. Salt crystals don't. So some things are birefringent, some things are not. And you guys, when we go to CBST on February 3rd, you'll have a chance of using all these techniques. This is from last year, the class, and each student brought, and we took images of it. You guys are going to do the same thing. I'll be telling you more about it next week. But you'll be able to use bright field, dark field, polarized light microscopy on your own sample that you decide that you want to look at. Okay? You can also use reflection microscopy. Some people there use reflection, some use dark field, and some use bright field, and some use polarized. Okay? We even have hot cocoa done under fluorescence. So you guys, when you get a chance, take a look, because you will be doing more with microscopy. Okay, so just to show you, you guys remember, I think I showed you early on C. elegans. Did we see C. elegans so far? Or no, I can't remember now. Little tiny nematode worms. Oh, I guess you guys haven't seen them yet. You will be seeing them. I think you'll start seeing them on Monday with Anna. But these are tiny little worms that whenever you guys have a picnic, you're sitting on hundreds and thousands of these. Okay? When they're fully adult, they're about the length. Their full length is the thickness of your fingernail. Okay? So full adults are about 1 millimeter long. But they're these little nematodes, these little worms that live in the ground. And when you look at them in bright field, they look like this. When you look at them in dark field, they look like that. When you look at them under something called phase contrast, they look like that. When you look under polarized light, you see their musculature. If you have them labeled so that they're polarized so that they glow where their nuclei are, you see this. And if you take all these images together and merge them, you can see different things about something, a biological system, by using different microscopies and overlaying them together all in one image. Okay? So different types of microscopies give you different information about your sample, is the main message. And what's fluorescence microscopy? Well, in fluorescence microscopy, we shine a light, like a blue light. We have it hit a mirror, go through the objective lens, hit our object. The fluorescence coming from that object comes back, is passed through, and that's what we see. So this mirror here bounces blue light and blocks blue light from coming back. So you can imagine this blue light would also be bouncing off this object, because not all of it is going to be absorbed to cause fluorescence. But this blocks it so that only the fluorescence comes through, and that's all I see. So what's interesting about fluorescence is, where's Waldo in this image? Anyone see him? Can you describe?
Besides the white balloon in the center behind the people, one guy with orange shirt, the girl with the
Right here?
shirt. Yeah.
Good job, guys. Good job, guys. But I could have made this a lot harder. So what can we do to make them easier to spot? Well, we can stick a big arrow on them, but that's not the easiest thing that you can do on an actual living cell. So what we can do is we can make them fluoresce, such that when I turn on the blue light, he's the only one that glows. Okay? So now you notice I've taken a scene that was very complicated, had a lot of different things in it, and I've brought out the thing I want to study. And that's the same thing we do with fluorescence microscopy. We can use a whole bunch of different colors. This is showing you different fluorescent dyes. Okay? They're saying, and these are all of them, this one, if you excite it at about 640 nanometers, it glows red at about 670 nanometers. If you excite this at 568, it glows at 570 something. Green fluorescent protein, if you shine blue light on it, it comes out green. Okay? There's lots and lots. There's hundreds now of different dyes that you can use. And if you can selectively attach them to the thing you want to study, then you can make just those things stand out. So, to give you an example, here, actin filaments are shown in red. They've been labeled with a red fluorescing protein, microtubules in green, and the nuclei are in blue. So when you see these pretty colored pictures of cells, what they've done is they've selectively labeled different parts of them. Okay? So they can emphasize those parts. And another technique in microscopy I just wanted to mention is something nonlinear structured illumination. I'm not going to talk a lot about this now, but because you'll be seeing this when you come on the tour. But what it does is it allows you to get much higher resolution than we thought was theoretically possible. And it does this by something called moire patterns that say that very, very fine structures, when you overlay them at different angles, can amplify, can let you see fine detail as a larger kind of phenomenon. So what we do is we basically shine a pattern of light onto the sample and we rotate it. And you get kind of, I don't want this one to go right. No, I want this one to go. Why aren't you going? This is showing you a red mesh and a green mesh, that when you move them on top of each other, you get other patterns. And if you use a computer and you study these patterns, on top, you don't know on top of the one that you don't know, you can use a computer to figure out more about the pattern you didn't know. Here's another example. Oops. This is a situation where there's a pattern underneath that has the number 2. We know the pattern on top. And you guys kind of see a 2 in there? And you see how it grew bigger and smaller? So you can see small things in the underneath layer by doing this manipulation with the upper layer. So that's how that technique works. You'll be hearing more about it as we go through it. So the other example I wanted to show you was the eye. Now let me show you this first little video.
As light enters the eye, it strikes the receptor cells of the retina, called the rods and cones. A chemical reaction results in the formation of electric impulses, which then travel to the brain through the optic nerve.
Okay, so did you guys see that? So the light comes in through the cornea and the lens, hits the retina, it goes through several layers of cells, activates or hits rods and cones, which have molecules in them that will change shape when they interact with the photons, which will then trigger an electrical signal that goes into the brain, and which we then interpret as vision. Okay? To tell you a little bit more about that, we have 4 different pigments in our eye that detect vision, and those pigments are a blue pigment, heavily sensitive in the blue part of the spectrum. We have a rhodopsin, which is what we consider our black and white vision, kind of our night vision pigment. We have a green pigment, and we have a red pigment. These three, the red, green, and blue, are in the cones, or I think of it as cones for color vision. And this one, the rhodopsin, is actually in the rods. That's our night vision, okay? But this is the region of the spectrum that they're sensitive to. This is what will trigger them to sense light. Now, this is the eye, and these sensors are inside these rods and cones, which are lining all the inside of the retina, okay, in the back of your eye. Okay? Now, something that we've talked about before, do you guys remember how which one looks brighter? The green, okay? Even though these two things are the same power, the green looks brighter. That's because our perception of color, even though we have sensors in the red, green, and blue, and also in this yellow area of the spectrum, and they all look equal, this is just their sensitivity. Our perception of color looks more like this. So when we look at our green laser, this is a line right here that is for our green laser. Our eye is quite sensitive to that light. Our red laser is down here. So you notice the sensitivity here is about a tenth of the sensitivity in the green. So if I had a red laser that I wanted to perceive as equally bright as a green laser, I'd have to have it be 10 times more powerful. Okay? So our eye is most sensitive. This is for daytime vision, by the way. Our eye is most sensitive in the greenish yellow. Okay? And that corresponds to the maximal output we get from the sun. Believe it or not. We're kind of tuned to our sun. Okay? We don't see blue as well, and we don't see red as well. We're not as sensitive to those parts of the spectrum. Yes?
They reversed stoplights and made the red mean go and the green mean stop, and we have like less people running red on accident.
Well, what they end up doing is, believe it or not, what caused less accidents was just having the lights switch faster, which is what happened when they switched them to LEDs, because they didn't have to wait for a filament to heat up. But the red LEDs have to be, for us to perceive them as equally bright, you have to put a lot more power into the red LEDs. They have to be much brighter. They have to be much more powerful in terms of the amount of light they give out for us to perceive them as equal brightness. Okay. Well, you might still perceive them as somewhat brighter. I mean, the thing about red is we have a natural built-in response to red because of fire. So to us, red signals danger. So it's pretty, that's a good thing, whereas green is like, nice rolling green fields, all this kind of stuff. So to switch those would create quite a other problems.
Is it true that the light doesn't dilate your people in the dark?
Yeah, and the reason for that is when you're in the dark, this is the only active photoreceptor, rhodopsin. And if you notice, rhodopsin isn't sensitive 600 to 700. It just has no sensitivity. So what that means is that I can blast red light, and the red light will only activate my red photoreceptors for my daytime vision. I can make really, really bright red light, and I'll still see things with that red light using my cones. But my rods will not have been affected, so I can still have night vision. If I were to use a green light to do that, I'd be messing with it. I'd be kind of saturating, I'd be activating my night vision rods when I wouldn't want them activated, because I want to be very sensitive to very minimal amounts of light.
That's why in like naval ships and stuff at night they'll go to red lights.
Yes, exactly.
So the guys up on watch on black.
Exactly. Same reason why if you're an astronomer or you want to go out stargazing, the thing you should do is you should bring a red LED and shine that on whatever you're looking at, your reference, or if you're reading something, you want to use red because it doesn't activate your night vision, and then you can still be very active and be very good at seeing in night vision. Now, the thing that I don't show here is that this sensitivity curve shifts over towards the blue by about 50 nanometers for night vision. So believe it or not, at night, we have more sensitivity in very low light. In low light conditions, we have more sensitivity towards the blue part of the spectrum much more than we do towards the red. But this is the daytime sensitivity. So this just shows you, this is a blow up of a rod, and inside the rod, you've got all these membranes, plasma membranes, and inside them you have these things called rhodopsin molecules. That's the photoreceptor molecule, right? That's the molecule that actually reacts to the light. And what happens there is, see this little part here with the molecule inside, this is a blow up of that. This is the membrane here, and this is your rhodopsin molecule in here. And inside the rhodopsin molecule, there's something called 11-cis retinal that in the dark has this shape, and in the light, when a photon hits it, it straightens out. So that changing of conformation is based on the absorption of light of a certain range of wavelengths. It changes the molecular shape, which then causes an electrical signal. If enough of those are activated, change shape, cause an electrical signal, which then goes to your brain. Okay? So the photons cause a structural change from a kinked to a straightened molecule. Enough of those cause an electrical signal, which then your brain responds to. Yes?
How long does it take for that change to be effective?
You know, it's at least faster, the whole process from the stimulus to us sensing the stimulus and registering it is faster than a 30th of a second. Exactly how fast that particular piece is, I don't know. It's a chemical, this should be really, really fast, this type of transition. It should be much faster than, I would think it would be microseconds, if not faster. But the whole response, there's a lot of chains in the response. The other thing about the eye that's really interesting, and you guys have those little blind spot demo pieces that you can do later, and you can see where your blind spot is that basically, if you look at the distribution of cones and rods, in the center of our vision is where all of our cones are. So we have fantastic color, sharp color vision in the middle of our visual field. But we're lousy as we go off to the edges. Okay? So believe it or not, you don't have very many cones over here to sense color or shape. I don't know if you realize this, but when you're looking at something, you have a very sharp little circle that you can see well, and then the rest is actually quite fuzzy. The reason you don't think of it that way is because your eyes are constantly doing this. They're constantly moving and flittering, and the brain is keeping track of that information, making you think that it's relatively sharp. But in reality, even if I look right here, if I'm looking at you and I look over here, it's already fuzzy. Okay? Now, what we do have over there is lots of rods, which are sensitive to low light and are more of our black and white sensors. So if you guys ever notice when you're out stargazing in the night, you actually see brighter things on the edges. You see more on the edges than you do in the very center of your vision. Yes?
That one at night or two, it says optimal, and it kind of disappears. So you can see the rest of it.
Huh. I haven't thought about that. Probably. You don't have, if you're looking at a single spot kind of thing, but if it's bright, then it's activating your cones. If it's dark, then it won't, and then you wouldn't be able to see it very well, and that might cause what you're saying. But if it's bright, I'm not sure. That could be a different effect. Okay? So, just to give you a sense, there's roughly 125 million rods in your human retina and about 5 to 7 million cones. Okay? There are no rods whatsoever here in the center, because everything is your color vision. It's all your cones that are doing that. Okay? So you have about 16 rods for every cone, and there's only about 1 million separate nerve pathways from each eye to the brain. So the average path that goes from your eye to the brain has to carry information from 6 cones and 100 rods. Okay? So your brain is doing a lot of processing. There's a lot of processing going on even before the image ever gets to your brain. Because if I were to look at this and say, oh, we only have 1 million separate nerve pathways, we can only sense, we're only a 1 megapixel camera. Okay? But in reality, the way we're concentrated and we have a much higher density in the center and the way things are laid out, it appears like we have a much higher resolution image than if we were to just use a simple idea of a camera. Our eye is quite more complicated than a camera. The other thing to think about is that each one of those receptor cells, rods and cones, so we've said that we have 125 million rods and 5.7 million cones. In each one of them, there are about 10 million photopigment molecules. Each one of them. okay, that are there, ready and able and waiting for a photon to hit them. Remember how we saw that membrane with all those rhodopsins inside it? So we have a huge amount of molecules in each eye that are sensitive to light and respond to light. And just to give you a sense, our best guess is that our eye is roughly gives us the equivalent power of about 120 million pixels. So gives us even though it has only 1 million nerve pathways, it gives the effective resolution and information of about 120 megapixel camera. Okay? Right now, the cameras you guys are using might be somewhere between 5 to 10 megapixels. So we're getting closer to what we think the resolving power of the eye is. And this is just comparing your old TV before we went digital was 168,000 pixels of information. And your new TVs now are a couple of megapixels of information.
So it would be used to create resolution better than the human eye if you would just see the human eye regardless?
Well, the only reason why we go to, there's already gigapixel cameras. People have made cameras that capture 1 billion pixels of information. But there is more information there than we could perceive. But a lot of it depends on how it's displayed. But the reason we do that is because we can still zoom in. So I could take a picture, out on the quad, and I could see how many hairs were on your head, by zooming in, kind of thing. That's why people still do it. So for satellite kind of imaging and all that kind of stuff, it's still worthwhile. But we can't perceive all that information at once. There's just no way. Okay? So with that said, I'm going to stop here, and we'll actually also do the CCD next time. We'll do the CCD and the spectrophotometer. And let me check that date for when pieces due. The other thing, guys, is we have to start thinking about your teams for your project. And starting next week, we actually want to get into that. But you should start thinking about what team. You need to have about at least 4 people in your team. So you will need to nominate a captain. So you probably should start thinking about who do you want to be in your team and who do you want to be the person that can come here at 10 o'clock on Fridays, for a couple of Fridays, to gather information related to your projects. Okay? So next week, by the end of next week, I'll be asking you for your formal team designation, who's on your team, and who's the representative that will come here for Friday morning meetings. Okay? Now, in terms of when is that other piece due?
You gotta take $5. You gotta take $5.
Just within the class. Okay, so you guys, your copies are due in 1 week, okay? Your reviews are due in 1 week. Okay, thank you guys.